Hi everyone, this is the second of the week 10 lectures on testing for interdependence. In this video I'm going to talk about cluster analysis, using cluster analysis with discriminant analysis, and I will make a few notes on structural equation modeling, but I will put up a separate video on that demonstrating how it's done. So to begin with, cluster analysis, what is it and why do we do it? So, cluster analysis classifies or segments objects, so customers, products or market areas, into groups. So unlike factor analysis, which groups items into constructs, cluster analysis groups respondents or the things that were being measured into groups. Cluster analysis is most commonly used in creating market segments and identifying potential target markets. So it's most commonly used with metric variables, but there are non-metric adaptations. So the procedure to do a cluster analysis is on the right. We're going to be looking at two variables in terms of creating clusters of people on these two variables. However, you can use more than two variables to create a cluster of people. So, to do the cluster analysis, I go to Analyze, Classify, and Hierarchical Cluster. I need to reset because I was practicing earlier. So I then select friendly employees and competent employees, or perceptions of these two variables, and put them into the variables box. I then go to method, and on cluster method I need to select Ward's method, which is the last on the list, and I say continue and OK. So the output for cluster analysis is really long and complicated. So as you watch, I'll show you how long the table is. So in interpreting this table, it basically looks at you start at the bottom and you work your way up. What this table says that if you go from having one cluster, like none, you have 747 points of error unexplained. If you go to two clusters, you have 334 error unexplained, so on and so forth, until you end up with, because we had a sample size of 200, until you end up with 200 different clusters. And while you have no error, you also have 200 clusters that are all individual, and you have not summarized or grouped your people in any way, your respondents in any way. So that's how this works. So in order to show you how to do a more thorough analysis, it's the agglomeration table. We need to look at the bottom first, and we look at the coefficients column, which is this middle column here that I've labeled in orange and said A. So as we go up the rows, we are reducing the number of clusters by 1, and this coefficients column tells us how much error we are reducing or explaining by having one cluster versus two clusters versus three clusters. So in this case, if I go from one cluster to two clusters, I reduce the error from 747 to 341, which is a reduction of 405 error points. If I go from two clusters to three clusters, I reduce the error from 341 to 258, which is a reduction of only 83. So how many clusters exist in our data set? Well, there are no hard and fast rules here. So the best number of clusters is determined by the researcher as you go from 1 to 2, 2 to 3, 3 to 4, in terms of what is the reduction between the clusters, because the greater the number of clusters, the increased, the less error that you have, but you have also decreased your summary power of your clusters themselves, and you're more likely to get overlaps between your clusters. So just for this purpose, I'm going to go with 2 clusters, as the proportion of error reduction after 2 is quite low. So when I go from 1 to 2, I've reduced by 405 points, but when I go to 2 to 3, it's only 83. So that's less than a quarter of the error being reduced when I go from 2 to 3 in this table, or 2 to 3 in terms of number of clusters. So I'm going to go with 2. So how do I then figure out what is going on in my 2 clusters? Essentially, I need to rerun my hierarchical cluster, but I then also need to click Save and select Single Solution, and then tell it that the number of clusters I want is 2. So to do this, I go to Analyze, Classify, Hierarchical, and I want to hit Save, Single Solution with 2, and I say OK. If I'm less sure about my 2, I can do a range of solutions. So if I wasn't sure if 2 or possibly 3 were the best cluster outcomes, I can run this second analysis with a range of solution where the minimum is 2 and the other one is 3, and it'll give me 2 different outputs that I can then test against. But in this case, I'm just going to do 2. So I hit Continue, and then I say OK, and I get the agglomeration table again. But more importantly, what I get is, in my data set, I get a new variable called cluster, or CLU2 underscore 1. And if you look at the data view on this, we have individual respondents now assigned to either the first cluster or the second cluster. So what I need to do now is look at what is the difference between cluster 1 and cluster 2 in terms of these respondent characteristics. How did we end up with these 2 clusters? So here I need to do a one-way ANOVA. So I go Analyze, Compare Means, one-way ANOVA. What happened to my... Oh, it's over here. Okay, for some reason. I need to reset. So I then put in my dependent list, the original variables I used to create the clusters to begin with. Oops, I did that wrong. I use Control and Select, and then the factor that I'm using is the new cluster, which is labeled Ward method, which has the 2 clusters of 1 and 2 in it. I then select Options, and I select Descriptive and say Continue and OK. So here is my ANOVA output, which I then analyze using the same ANOVA procedure as before. So we have our ANOVA table with the significance of whether there is a between group difference between friendly employees and competent employees, and we see that the significance between my 2 clusters for the friendly employees is significant, and the difference between competent employees is also significant. So there is, on both of these variables, my 2 clusters have significant differences in explaining people's responses here. Then I need to look at my mean table. So if you look at cluster 1's responses to friendly employees, they're 2.93. In competent employees, they're 6.96. So I can say that cluster 1 considers the employees unfriendly but somewhat competent. If I look at cluster 2 responses, on friendly employees they're given 4.5. On competence it's quite high at 9.36. So how I describe my cluster 2 is these are customers who think that the Delhi Depot's employees are somewhat friendly, but that their employees are highly competent. So now I have described my 2 clusters in terms of the variables I use to create them. I'm sorry about the jackhammering if you can hear it, but ANU is under construction. So how can I then use these new clusters of potential target customers with discriminant analysis in order to be able to predict what other variables will describe membership to these clusters? So that's what we're going to do now. So we use the cluster description as label values, and then you can combine with discriminant analysis and use the results of this cluster analysis solution as the dependent variable in a discriminant analysis. So the procedure here is as follows. I go to Analyze, Classify, Discriminant. I reset. I need to put my new cluster variable that was created, cluster 2_1, labeled ward method, into the grouping variable, and I need to define range. So in this case they are coded as 1 and 2, and then I hit continue, and then I'm going to select the independent variables. Some of these are metrics, some of these are not. So I'm going to select 6, 7, 8, 9, and 10 and put them in the independence variables box. I then need to select statistics, and I need to select means and univariate ANOVAs, and I select continue. And that's all I need to do, so I select OK. So we have quite a bit of output with the discriminant output. I'm just going to put this in the slides so it's more easily able to discuss it. So same with our analysis of discriminant output as we did last week. The first thing we need to look at is the Wilks lambda to assess whether the discriminant analysis is statistically significant, and a significant level is 0.000 with a Wilks lambda of 0.368, so therefore it's less than 0.05, it is significant. On the extra note, our eigenvalue 1.72 is okay, but if we look at our effect size, our canonical correlation squared is 0.632, meaning 63% of the variance is explained in our independent variables. So we do skip B because we have included non-metric variables in our independent variables list. So we're skipping step B and going on to step C on the discriminant analysis process. And looking at, of the 5 independent variables I included in my discriminant analysis, which ones predict memberships to cluster 1 and cluster 2. So this is the first step of this procedure. So we look at the test for equality of group means and significant levels over in the right hand column. As we see, all of our variables are significant in predicting differences between cluster 1 and cluster 2. So at this stage, all variables remain in the analysis. We then go on to the second part of this analysis and look at the structure matrix, where any variable that scores above 0.3 and an absolute value is a good predictor of cluster membership. And as we can see in our structure matrix table, all 5 of the independent variables, Fast service is the lowest at 0.338. They are all above 0.3, so again, all variables are good predictors of cluster membership between 1 and 2. So we are keeping all of our variables in the analysis. And then finally, in terms of describing who is likely to be a member of each cluster based on these 5 variables, we look at the group statistics. I've color-coded them this time round, but I've also summarized them on the right. So, in terms of fast service, people who score higher on fast service are likely to be members of Cluster 1. Cluster 1 is also more likely to be female, noting that gender is coded as 0 and 1, so males are closer to 0 and females are closer to 1, or are 1. So here we see 0.05, closer, more likely to be male, 0.68, more likely to be female. In terms of recommendation to a friend, we see Cluster 2 scoring higher as a higher mean, meaning that those who score who are more likely to recommend to a friend are more likely to be members of Cluster 2. Similarly, satisfaction levels, people who are more likely to have higher satisfactions are likely to be members of Cluster 2. And in terms of usage, this was coded also at 0 and 1, where low usage is 0, so 0.36 is closer to 0, and 0.91 is closer to 1. So Cluster 1 is likely to be low users of Deli Depot, whereas Cluster 2 is likely to be high users of Deli Depot. So here you can see the building up of a profile of Deli Depot customers into 2 distinct clusters based on these 5 variables, and also including the 2 variables that were used to create the clusters to begin with in terms of moderate and high assessments of employee competence and friendliness. So just to conclude, that's cluster analysis and how it can be used. In terms of structural equation modeling, I'm just going to make a few comments about structural equation modeling, what it is and why it is used. So a structural equation model is used to analyze what we call structural relationships. So it combines factor analysis and multiple regression, and is used when we have it can be used when you have multiple dependent variables. All of the analysis that we have done to this point assumes that you can only have one dependent variable. You can have, in regression and in ANOVA, you can have multiple independent variables, but you can only ever have one dependent variable. So in structural equation modeling, on the other hand, you can have multiple dependent variables. However, it does assume that you have a big sample size, and the more relationships and the more variables you are including in your structural equation model, the bigger the sample size needs to be. So the example I'm going to show you here is one from my PhD, where I looked at the relationship between celebrity worship and fan behavior. So my proposed conceptual model was that celebrity worship leads people to be more highly involved in the brands that the celebrities were associated with, and also to have higher identity salience with the social groups of other fans of that brand. And being more highly involved leads to greater brand commitment, and being more highly involved in more identifying with a fan group is more likely to lead to you to being members of the fan group in the future. So here we have the model, and as you can see from here, from celebrity worship to brand involvement, if I was trying to do a regression on just this section of the model, I would have to do 2 separate regressions, because this is my independent variable and these are my dependent variables. So that because there's two, I would need to do these as two separate equations. Similarly with brand involvement, social identity, and to future intention, if I wanted to do this analysis, it would be multiple regressions testing each one of the hypotheses separately. However, in a structural equation model, sorry, this is just some explanation of the items themselves. In a structural equation model, it tests all of the relationships simultaneously. So here is the information if you're interested in terms of where the scale items came from. I used all pre-existing scales in measuring my, my constructs. So here is the output from my structural equation model. So celebrity worship is composed of both cognitive and affective components, and as we can see, it has a 87% effect on both brand involvement and social identity and salience. Simultaneously, it has a 62% effect on brand commitment. Social identity salience has a 41% effect on future membership intention, and brand commitment has a 35% effect on future membership intention. So we have overall model fits. So this, because these numbers here are above 0.9, we say that we have a very good model fit. Because this RMSEA is below 0.05, again we say we have a good model fit. So this suggests that I have a good fitting model for the overall effects of these relationships, and all of these individual relationships were also significant and had, so they're also significant relationships, so therefore these constructs have a significant effect on the dependent variable that comes after them. So that is what a structural equation model is. There are other types of structural equation models, but while I don't expect you to do one in this subject, these are very commonly used in marketing research in the industry setting because of their explanatory power to explain relationships between complex ideas and constructs. So that ends this week's lecture videos. I will put up an example of how to do a structural equation model if you would like to view that one.